Welcome to qnawire.
In this problem, we're going to talk about static equilibrium. So what we need to remember is that the sum of the forces acting on a body for it to be in static equilibrium must be equal to zero, as well as the sum of the torques on the body. So both must be equal to zero. So that's what we're going to apply. So what we have in our problem is a beam that is supporting a street lamp, and the beam itself is supported by a cable represented here in the figure in red that makes a right angle with the beam, and also a pivot uh, represented here in black. Okay, and our goal is to find, given that the length of the beam is 4.5 meters, uh, the distance between the pivot and the center of mass, the center of gravity, I'm sorry, of the beam is 2 meters, and the distance between the pivot and the place where the force, the cable force, is applied is 3 meters. And also, we have the information that the tension on the cable is equal to 5. I'm sorry, not the tension on the cable. This is the force that the street lamp exerts on the beam downwards is equal to, in magnitude, it's 5 kilonewtons. And I wrote it with a minus sign here because I'm setting up a coordinate system where the y-axis points upwards and the x-axis to the right. Okay, so the weight force is equal to minus 1.4 kilonewtons in the j direction. Okay, uh, so now we can go on, and our goal is to find the magnitude of the tension and also the horizontal and vertical components of the force that the pivot exerts on the beam. I'm going to call that force P. Okay, so I'm going to start with the torque equation. So notice that I'm going to draw a force diagram, free body diagram on the beam. So we have first the gravitational force, mg, acting at a distance of 2 meters from the pivot. Then we have the tension force acting at a distance of 3 meters from the beam. And we have the force F from the street lamp that that is acting at a distance of 4.5 meters from the pivot. Okay, and also uh, there is a force, the pivot force, that's pointing somewhere. Uh, I'm not sure where yet. We're gonna find it out. I'm just gonna draw it here somewhere. It's pointing somewhere basically, and it has magnitude p. And now I can write the total torque. So the total torque is equal to, first notice that the torque will always lie in the z direction here, in the z axis. By the right hand rule, notice that this angle here, first of all, this angle here is 25 degrees. So this means that this angle here is 65 degrees. So is this angle here. So by the right hand rule, um, the torque caused by F and mg are counterclockwise. I'm going to call that positive. So, and the torque is equal to F. The magnitude of the torque is F times sine of theta times the distance. So F, L is the total length of the beam, times sine of 65 plus mg times d times the sine of 65 minus t H is the distance to the point where the tension is applied. And notice that here, the angle is just 90, so the sine of 90 is 1. And I wrote it with a minus sign because by the right-hand rule, it's pointing in the clockwise direction. And this must be equal to 0. So T is FL sine 65 plus mg d sine of 65 divided by h. Now, F is equal to 5 kilonewtons. L is 4.5 meters. Then you have to multiply by the sine of 65 plus mg, that's the weight of 1.4 kilonewtons, times d times sine of 65 divided by h, and h is equal to 3 meters. So T is equal to 7.64 kilonewtons. This is the magnitude of the tension. Now notice that we have to find the force P that the pivot exerts. So I'm going to write T in the vector form so that we can find P. Notice that T is such that this angle here is 25. So this angle here must also be 25 degrees. So we can write T as minus T times sine of 25I plus T times cosine of 25J. So using that T is 7.64 kilonewtons, we obtain that T is minus 3.2I plus 6.9J kilonewtons. This is the value of the tension T. Now notice that the sum of all the forces, that is the weight plus P plus T plus F is equal to 0. And we want to find P. So P is minus T plus F plus W. Now T is minus 3.2I plus 6.9J. F is minus 5J, and W is minus 1.4J. So this is equal to 3.2I minus 0.5J. So the horizontal component is 3.2, and actually I forgot to write here, but this is in kilonewtons. The horizontal component is 3.2, and the vertical one is minus 0.5, which concludes our exercise.